Hi everyone, thanks again for tuning in. In this video, I want to follow up with the user's question regarding how to estimate parameters from the AMH family of copulas. To quickly recap, recall that we discussed in lesson 8 a method of estimating the copula parameters by first computing the Kendall's tau of the data and then inverting that function to find the copula parameter. Today, I want to show you a method for how to do this with the AMH copula specifically. So let's start by taking a look at the relationship between Kendall's tau and the parameter for the AMH copula. And that's given by this expression right here. If you're interested in the derivation, I've provided a link to the research paper here. So it's immediately observable that inverting this relationship is not trivial. So to step back a little bit, we can generalize this to say that given a value of theta, of the copula parameter theta, we can apply this expression and get a value of Kendall's tau. And this is the relationship mapping these two. But what we want is to give a value of tau and derive a value of theta. So this is basically what we want to do is invert this function. And like we just discussed, inverting this analytically is not trivial, but there are a lot of numerical tools that Python gives us that can help us to do this in an automated fashion. So before we jump to inversion, let's first plot out the relationship between the copula parameter theta and the value of Kendall's tau. And I just want to point out that because theta is in the denominator here, we have to be careful about 0. And so we don't want to have any divide by 0 errors, but otherwise, this function, AMH theta to tau, implements this expression here, taking into account division by 0. So now that we have defined this function, we define a vector which is all of the possible values of theta, and for the AMH copula, that goes from -1 to 1, excluding 0. And what we want to do is apply this function to see what are the values of tau that are possible. And this relationship is plotted out right here. And I show the two regions of the negative values and the positive values, and I show this discontinuity as well. All right, so that's the relationship for the AMH copula between theta and tau, and now we're trying to invert it. So how would we do this numerically? Well, there are several approaches that we can take. The simplest would be to build a numerical mapping between theta and tau, and then find the closest value of tau for a given query and map that back to theta. So this is kind of like a lookup table approach, and it's certainly valid and very fast in practice. But today, I want to show you a different way of doing this that uses numerical optimization. So in numerical optimization, or just in optimization in general, we phrase all problems in terms of minimizing an objective function. So what we need to do is transform this problem of inverting this function into an objective function such that the minimum value of that objective function will give us the answer that we want. And so there are probably many functions that can satisfy this relationship, but today we'll use one called mean squared error. And so let's derive this objective function from this original relationship right here. So you can think of this function as y equal to a function of x, or tau is equal to a function of theta. So what would happen if we subtracted f of theta from both sides? Then we would get tau minus f of theta is equal to 0. And that's the first, so we start with this tau equal to this relationship, and then we say, let's subtract this second part from both sides of the equation. And what we get is tau minus this expression is now equal to 0. So now remember that we're going to use an optimizer, which tries to minimize a function that we give it. So we're trying to find the optimal function to minimize. So theoretically speaking, if I'm trying to minimize this function, there might be a value of tau and theta such that it is less than 0. But what we want is we want the minimum value of the objective function such that the answer is exactly equal to 0. And so we can achieve that. We can achieve this equality by squaring this error term. So we can think of this as an error between the actual value of tau and theta such that it satisfies this relationship. And what we want to do is square this error such that the minimum value of this error corresponds to an equality of this relationship. And this is getting more into optimization, so I don't want to go into it too deeply, but that is the basics of how we derive this objective function here. So we define this objective function O is equal to tau minus f of theta squared. Then what we can do is we can basically code up this objective function directly. So we haven't done any actual analytical math here. We've taken the original expression, f of theta equal to tau. We've subtracted f of theta from both sides, and then we squared it for optimization purposes. And then we implement that function here. And then now we can use numerical optimization techniques provided by scipy. So here I'm using this specific function called minimize scalar in the scipy.optimize package. And here are two examples of how you can do this. So let's say we want to find the value of theta when tau is 0.2. So we can kind of eyeball this and say, oh, if I take my mouse cursor to y equal to 0.2 and I put it over, I can see that the x value is somewhere between 0.5 and 0.75, closer to 0.75. So what does the optimization tell us? So let's define the value of tau that we want to find the value of theta for. And then let's call this minimize scalar function on this objective function that we created. And I specify the kind of optimization that I want because we have this discontinuity at 0. So remember that if the value of tau is greater than 0, then the value of theta is also greater than 0. So we want to bound our region of optimization from 0 to 1 because that's the range of possible values that we can get. And so we specify that here, and then we run the actual optimization. And it says, oh, solution found, and the value of x is 0.71. And that corresponds to what we saw in the graph as when tau is 0.2, we get a theta value somewhere between 0.5 and 0.75, closer to 0.75, and the optimizer said it's 0.71. So now we can do the same thing for the negative side. The notable difference here is that we have to specify the negative bounds because remember that when tau is less than 0, theta is also less than 0. So that corresponds to this blue section here. So we provide this bounds and then we run it and it says when tau is negative 0.1, theta is negative 0.5. And that roughly corresponds with what this graph is showing. And just to top it off, I actually plotted the values that the optimizer finds for given a value of tau, what value of theta did you find? And these are plotted with these red stars here, and you can see that it's right on the money. So we can see from this graph that this sort of optimization approach seems to be working. So you can, in general, use this sort of methodology of converting a problem, in this case of inverting a function, into a loss function, and then using numerical optimization to find the solution. So thanks again for tuning in. I hope this helps, and feel free to leave some comments, additional questions, and suggestions for future videos below. Thanks again.